everyone. My name is Kimberly Bennett. I'm a medical engineering PhD student in the Hammond and Schuyler labs here in the KI. In the KI, there's this constellation of people. There's biologists, there's chemists, chemical engineers. But as a medical engineer myself, I think a lot about this question. How can combining science, engineering, and medicine help patients? And so today I'll talk to you about one such way related to one of the most important organs in your body, the brain. So your brain is this incredible organ that's responsible for so many functions, from regulating your heartbeat, to controlling your breathing, to commanding all the nerves in your limbs on how to move and when to move. And to power this organ, you need a network of blood vessels that are needed to deliver blood and oxygen to your brain. And so in the brain, these blood vessels, made up of endothelial cells, are also accompanied by other cells like pericytes and astrocytes. And so this combination of endothelial cell, astrocyte, pericyte, or these kind of special blood vessels are what we call the blood-brain barrier. And so the blood-brain barrier gets its name for its important role. It needs to selectively allow nutrients, oxygen, all those good things to get into your brain tissue, so out of the vessel and into the brain. But when it comes to nasty things like pathogens, bacteria, or other things that you wouldn't want to get in the brain, it needs to act as a barrier to prevent them from leaving the blood vessel and prevent them from getting into the brain tissue. However, there's one big downfall about this blood-brain barrier. It's a little too good at its job. So what does that mean? Let's consider this. A child is diagnosed with a rare brain tumor, such as diffuse midline glioma, a 100% fatal tumor, and the doctor wants to try to treat them with something like a chemotherapy. This drug would, in theory, be in your blood vessels, travel to the brain, get out of the blood vessel, and to the tumor site to then kill the tumor cells. However, in reality, because of this blood-brain barrier, this whole pathway doesn't actually happen. And so the blood-brain barrier prevents drugs from entering the brain. And so there was so much research, going into how this drug would work. Can it kill a tumor cell? Tested it in the lab to make sure that this drug could kill the cells. But when we took this drug and put it into patients, we didn't see that effect. And so there's this need, yes, to develop a treatment that can navigate that brain space to be able to get to the brain, out of the vessel, and to the tumor. But on the lab side, we actually need a model that we can use to test if these new therapies that can predict whether or not how they would behave in a patient. And so this is where my research comes in, and I create microvascular models to enable drug delivery. Essentially, what I do is I make a mini blood-brain barrier on a chip. And so for size reference, these little chips are probably yay big. And by combining multiple cell types, endothelial cells, astrocytes, pericytes, those cells that I mentioned make up that blood-brain barrier, and putting them alongside patient-derived tumor cells, so cells that came straight from a patient, I can actually recreate this kind of network of endothelial vessels on a chip. And so what this allows me to do is take, say, a therapeutic of interest, maybe like a nanoparticle that carries a drug, put that into a device, have that in your vessels, and test, can those get out of the vessels and to the tumor cell? And be able to mimic in the lab whether or not this drug delivery system would work. And hence that brings me to my image, where within a chip, we're seeing these microvascular or blood vessels highlighted in purple. And in those kind of circular dark spaces in between, you see a lot of speckled particles of something that in theory would have been able to leave the vessel and enter that tissue space. And so again, this is all within a chip, and it's all mimetic of what the human blood vessels in the brain would be like. And so To me, also, I think looking at kind of these, speckles in this dark circle is almost reminiscent of outer space in itself and the hope and wonder of what this technology could mean for drug development and designing a system that can actually navigate the brain space one chip at a time. And so, with that, I'd like to thank my advisors, Paula Hammond and Jill Estrela, everyone in the Hammond and Estrela labs, as well as my undergraduate students pictured below, who have helped me at various stages in this PhD. And so feel free to find me if you have any questions or scan the QR code for my contact info. And thank you for listening.